How's everyone doing? It's the 9th, and I am recording a lecture on energy for this coming week. It is storming outside right now. There's a low pressure center going right through, and it's given us some thunderstorms. It's pretty cool. So hopefully you guys are noticing that on Thursday the 9th that it's raining outside. Maybe you guys are still sleeping because it is only 1:30 in the afternoon. But it is a low pressure center and it's a cold front. So after this front moves through, the air that will be replacing our warm, nice, sunny air will be colder. And they forecast possible snow flurries for different areas because of that cold front coming through. So hopefully you noticed that. Anyways, I hope everyone's doing really well. What I'm going to do today is I'm just going to talk to you about energy. Now, this should be review. I'm going to go really fast. Essentially, this is going to be a review sheet for you to reference whenever I give you an assignment on energy. So I'll give you several different assignments, and all of the information will be on this sheet that you will need for each of those assignments. So hopefully that will be helpful for you. So energy, first of all, what is energy? Energy is the ability to do work. The ability to do work. And up until now, we've really broken down energy into three different chunks or three different categories. We've talked about different types of energy. Let's do that down here. We've talked about types of energy. We've talked about the transformation of energy. And we've talked about the transfer of energy. And this probably all sounds pretty similar. The transformation, the types, and the transfer of energy. But I think this will all come back to you really quickly. So the types of energy, by that, I'm talking about something like, well, let's see, solar energy. So using solar panels. Solar energy is our insolation. Insolation, this is something you're going to see next unit. But this is the incoming. The SOL stands for solar radiation. So this word insulation is not the insulation that we have in our house to keep our house warm in the winter. It's incoming solar radiation. Incoming, the IN, SOL is solar, and the ation is the radiation. So incoming solar radiation. And the solar energy, this insulation, is either light or UV. Those are the two dominant types of solar energy. We have things like heat energy. Heat energy. And the heat energy that we're going to talk about most is infrared energy. Infrared energy. Like if you look at heat, like a heat goggles, those are showing you the infrared energy given off by objects. And that's pretty cool. I'll have to see if I can find something like that on the internet and show you. Nuclear energy is another one. Nuclear energy. This is an energy we talk about when we talk about stars in the astronomy unit that we're getting to. When we're going to talk about nuclear fusion and nuclear fission, we're going to be talking about nuclear energy. Then, all right, we have kinetic energy. The energy of movement. All right, and we have something called the electromagnetic spectrum. And the electromagnetic spectrum is in your reference tables. Ooh, I'm not exactly sure what page off the top of my head, and I don't think I have reference tables handy, but I'll get that. It's in your ESRT, and I'll show it to you. Oh, I got it. Never mind. I had already written it down. It's on page 14. ESRT page 14. And on the electromagnetic spectrum, I'll have you guys do some things for me on that one. You're going to find that on one side of it, we have gamma waves. And on the other side of it, we have radio waves. And the gamma waves are really high in frequency, meaning there's a lot of waves in a lot of waves in a small space. So this would be a high frequency wave. To contrast that with the radio wave, that is what a radio wave would look like. Okay, so you can see that the wavelength of the radio waves are long. We have a long wavelength. That upside down Y is a lambda. It's long wavelength. That's what you'll see me use for wavelength. and it has a low frequency. So long wavelength, low frequency. And those gamma waves, you can see that they're really just the opposite of these radio waves. So they have a short wavelength and a high frequency. Okay. And everything is going to be in the center of these. So we're going to have microwaves. We're going to have visible light. We're going to have, we're going to have UV. All these are going to be listed in between gamma waves and radio waves. So this week, when I give you your assignments, you guys are going to have an assignment to do on the electromagnetic spectrum, where you're going to have to look at the spectrum and answer questions based on the frequency and the wavelength of that. Just one little side note before I leave you, you do need to know what a wavelength is, but I feel like I've already talked to you about this in class. Remember, we have wave height, which would be this right here. I think we talked about this when we talked about shorelines. And then we have wavelength, which would be from crest to crest. Does that sound familiar? Wavelength. Or trough to trough would be another wavelength. And we're using a lambda. So if we drop down, knowing that wavelength right here, if we drop down, here is one wavelength, crest to crest. See how short that wavelength is for a gamma. And then radio wave would be wavelength to wavelength. And you can see that it's much longer for wavelength of a radio wave. All right, so just start putting together the frequency and the wavelength for those. All right, transformation of energy is something that you guys need to know a little bit about. This is pretty important. What we talk about most with transformation of energy is kinetic to potential and potential to kinetic. So if we think about us on a roller coaster, here's us in our roller coaster, our arms are high, and we're thinking of us at different locations on that roller coaster. So here we are again. Okay. And what I want to think about is what our kinetic and potential energy is like at those different locations. So first, kinetic energy is the energy of motion. And potential energy, you probably already know this before, you're probably saying it with me, is our stored energy. So up at the top of this roller coaster, right when you're up at the very top of the hill and you're ready to go down, your potential energy is very high. You have the potential to go very fast, but at that point, you're not going fast. You're tipping that little peak and you're about ready to go down. So you have the potential to go fast. You have a lot of stored energy up at that spot right there. You could fall, but your kinetic energy is really low. You're not going very fast at that point. Now there's a transformation of energy as you start going down this hill. The potential energy now gets low when you're all the way down here because you're at a low elevation. You're not really high lifted off the ground, but you have a lot of kinetic energy. This is where your stomach starts to do a little flip and you have a high kinetic energy. So when you get down to the bottom of the hill, you have a high kinetic energy and a low potential energy. And when you're at the top of the hill, you have a high potential energy and a low kinetic energy. So it's this transformation of energy. When we do it in earth science, we actually talk a little bit about astronomy. And when we're orbiting a planet, this is our planet, and it's orbiting a sun. So this is the orbit that I drew. And we haven't gotten to this unit, but I just want you to see how we're going to use this. This is really important. When we get closer to that sun that we're orbiting, our kinetic energy is high and our potential energy is low. And then as we continue on in this orbit and we get far from this sun, so far versus close, at this point over here, we start to slow down a little. So our kinetic energy is low, but our potential energy is high. All right, so we have this transformation of energy that happens not only in a roller coaster that you'll learn about more when you're in physics, and this transfer from potential to kinetic, but we also have this same transfer of energy in our orbits in our Earth's orbit or any planetary orbit or any orbiting body, when it gets closer to that body that it's orbiting, the sun, a star, it goes faster, so its kinetic energy is high, and as it gets further away from that orbiting, its kinetic energy is low and it slows down. All right. The other type of energy or movement of energy I want to talk to you about is the transfer of energy. This is one that I think you did heavily in 6th grade. And this is really just energy moving from one molecule to another. Sorry. And while we're actually defining that, transformation was the change of one energy into another. Sorry. I jumped right into it. I'm trying to make this nice and fast. So change of one energy into another. So kinetic to potential, potential back to kinetic. All right, so back to transfer. We're going back to transfer. We have 3 that you know about, and I'm 100% sure you know it. Conduction, convection. We've talked about convection currents a lot this year. And then radiation is the last one. So conduction, convection, and radiation. Conduction is most easily transferred in solids and some dense liquids. And it's the transfer of energy by collision. So one molecule bumps into another molecule, which bumps into another molecule, which bumps into another molecule. Think of dominoes and the falling of dominoes. You set up a whole range of dominoes, you tip over one domino, and that domino bumps into the other one and knocks it down, which bumps into another one and knocks it down, which bumps into another. That's the transfer of conduction. It's actually the transfer of energy by collision. If you've ever thawed out meat, my husband was actually asking this the other day. We were thawing out a huge turkey, and it actually is faster to thaw in water. And he was asking me why. And I said, I think it has something to do with conduction. And I believe I'm like 99.9% sure that, even though we couldn't find it on the internet, or he couldn't find it, he didn't believe me. The fact that if you put a frozen piece of meat in water, the energy from the water will actually transfer by collision into the turkey. So the reason that it's quicker to thaw a turkey or a chicken or whatever meat you're trying to thaw, the reason it's quicker in water rather than leaving it out on the counter in the air is because of that conduction. You're actually putting it into a more dense solution, more dense than air. You're putting it into water, and that collision actually transfers the energy and thaws your meat quicker. So there's a little practical application that's helpful. All right, convection, liquids and gas. This is done with liquids and gases. Liquids and gases. All right, and this is the transfer of energy due to different densities. All right. So with convection, we have the hot source, or the hot making some liquid or gas rise up, and then once it gets away from the heat source, it's going to cool down and sink, and then heat again, cool and sink, and then rise up and heat again and cool and sink. So you get this convection current. And we saw this in the asthenosphere. We also saw it in the atmosphere around our Earth. So we've now done 2 units that have done that have taken into account convection currents. So I'm thinking you've got that by now. And then the last one is radiation, and this is the transfer of energy by waves. Transfer of energy by waves. So it can occur in empty space. So we have our sun. This is our sun. Our sun's waves actually get to us by radiation. So they've traveled through empty space to get to us through that empty space. So by radiation. All right, a few other things I want to just pop on the top of this. So this is, I'll just back up a little bit. This is the bottom of my sheet of paper, all right? Energy, the ability to do work. You need to know the types, you need to know the transformation of energy, and then you need to know the transfer of energy. There's one last thing that I'd like to do with you before I finish this video for today, and I'm going to use the top of my paper. All right, I would just like to talk to you about reflection, refraction, and absorption. That's something that's really quick. Reflection, again, I think that you guys already know this, right? Refraction and absorption. So the reflection, if this is our surface right here, the reflection is when a wave comes in and then bounces off that object the same way that it came. So this is one behavior of waves. Waves can bounce off an object and return the way they came. And if you think of something that's a surface, that's a good reflection, a mirror is perfect for that. Glass sometimes has a good reflection if the waves are coming off of the glass and bouncing back the way that they came. Refraction. The last time you heard me talk about refraction is when we talked about the layers of our Earth and the earthquake waves going through them. So do you remember the different layers of our Earth where we had the inner core and then we had the outer core and we had the mantle? That looks very ovalish. And then we had the asthenosphere around the outside. And we said that we could have an earthquake and those waves would go through each of these different layers. And when they went through, they would refract or bend. All right. And they'd bend when they went through those different layers. So that's the refraction we've already covered. For today, what I need you to know is that when waves come in, they're actually going to bend to a different angle. Okay, so if they came in at this angle, they're going to bend at a different angle and then come out the other side. Okay, so that was a poorly drawn diagram. Let me see if I can do it better with a different color. So let's have it come in at an angle and then it bends and then it comes out at a different angle. So what you end up with is sort of this shifting of your wave. It actually bends when it goes through a substance. Water does this. So water refracts objects. Water refracts the waves. So, or bends them. So let's write this down. Bending of waves as it passes through substances of different densities. So refraction is the bending of waves as it passes through substances of different densities. Sorry about that. All right, and then absorption's the last one. The absorption is simply when energy is taken in. By a substance. Energy is taken in by a substance. So you guys need to know, let's just draw it. We've got our wave coming in, and that's where it ends. It's taken in by a substance. Now, a good absorber, you need to know this. This is something that actually falls into the earth science curriculum. A good absorber is something that, well, takes in heat really easily. So let's think about this. If the sun is shining in the summertime and it shines on a good absorber, this is something that feels hot when you walk on it with bare feet. So you're probably thinking, all right, it's something that's dark in color. If you think about walking on your driveway in the summertime with bare feet, it's going to be really hot, right? So good absorbers are dark in color and rough in texture. I remember going to Hawaii with my family, and there were these black sand beaches. So it was rough in texture and dark in color. It was black sand. It was actually lava rock, and it was they were empty. Nobody wanted to go to those beaches because they were such good absorbers that they absorbed all the sun's energy, and nobody even wanted to lay on them because they were so hot. It was disgusting. They were so hot. All right, one last thing I want to talk about with you. Is just a little bit on the greenhouse effect. I'm going to just talk about that over here. So let's talk about the sun. We'll just draw a little picture. Here's our ground. Here's our sun. And the sun actually gives off mostly visible and UV light. So what I want you to see, is that this UV energy is coming down to the ground. UV energy, ultraviolet. UV energy, I'm going to do another one. Okay, and this ground has the ability to absorb the energy. But it doesn't just absorb the energy, it actually re-radiates the energy. So it re-radiates it. And when it re-radiates it at longer wavelengths. So let's go ahead and draw that. If it re-radiates this energy at longer wavelengths, then that's actually going to re-radiate this energy. See the length? This is a short wavelength. These ones over here coming off, the UV energy is coming off the sun at a short wavelength, high frequency. And notice the energy that I have re-radiating this is at a longer wavelength. This one is the infrared energy. You guys have actually seen this. This is what happens when you open up the grill and you can see the heat coming off of the grill. Or on a really hot day in the summer when you actually can see the heat coming off of your cars. It looks very distorted and like wonky and wavy. You guys can actually see this infrared energy. So the UV energy comes in from the sun. You can't see that, but you can sometimes on a good day see that infrared energy. So I want you to understand that when high wavelength is absorbed, it's re-radiated at a longer wavelength. So the ground absorbs the UV energy, absorbs our UV energy, and re-radiates it at longer wavelengths and re-radiates it at infrared. Now, if I just took a moment and actually talked to you quickly about this greenhouse effect or greenhouse gases, the greenhouse gases would be gases like CO2, CH4, I'm drawing a blank, H2O, and these would be like methane and sulfur. There's the sulfur one up there. All these greenhouse gases are right up here, and they're in our atmosphere. And those would be considered our greenhouse gases. Now, the thing is they actually trap these infrared energy. So they're able to let through the UV energy, but they trap the infrared. So that's important because the more we pollute our Earth, the thicker this layer gets. And this greenhouse layer gets thicker and thicker and thicker, which traps more of our infrared energy. The more energy trapped, the higher our climate temperatures go up, the global warming increases. Our average annual temperatures start to increase over time. So really, it's because of these greenhouse gases up here in the atmosphere being able to trap these long wave radiation waves that are being re-radiated by our ground. It's all a very natural thing, but what's not natural is this thicker layer here that traps more of that infrared energy, causing an increase in temperature. All right, so that was everything in a nutshell. I'm actually going to take a picture of this and just post it for you all, and I'll give you the ability to take a look at it and then have it as a reference. Okay, so that's what it looks like. You guys all have a great day. There's one more lecture coming up right after. Talk to you. Bye.